So, Kamar, is my screen is visible?
Yes.
Anybody?
Yes, Dr. Mukherjee.
Okay, okay. So, thank you. So, to our today's speaker is Dr. Bodhisattva Mujumdar. He is a professor, assistant professor in the Department of Computer Science, IIT, Computer Science Engineering, IIT Indore. So, it's a privilege to have Dr. Mujumdar with us. Dr. Bodhisattva Mujumdar received the MS and PhD degree from the Indian Institute of Technology, Kharagpur. He was a postdoctoral researcher with the Design for Excellence Laboratory, New York University, Abu Dhabi, UAE. He is an assistant professor with the discipline of Computer Science and Engineering, IIT Indore. His current research interests include optimized hardware implementation of cryptographic primitives, side channel attacks, and countermeasures, and design countermeasures against IP piracy and theft. He is presently a voting cum working group member, WGM, in IEEE standard 1413.1 on guide for selecting and using reliability predictions based on IEEE 1413 and IEEE 1624, which is the IEEE standard for organizational and capability. Dr. Mujumdar has been a technical program committee member of conferences such as VLSI, Space, and VDAC. So we welcome you, sir, again. So this is going virtually. So we try to felicitate all the speakers virtually. So it's a privilege to felicitate you virtually here with famous Gamcha of Assam and bouquet.
Thank you. Thank you so much. Thank you, Dr. Mukherjee.
Okay, sir. Thank you. Now you can start your session. You can share your PPT.
Okay. Can I take 2 minutes?
Yeah, no.
Okay. Hello.
Yes, sir. Yes, sir.
Hello. I'm visible. Okay, so I'm audible.
Yes, sir. You are audible.
Okay. Is my screen visible to everybody?
Yes, it's visible.
Okay. So thank you, Dr. Shyapada Mukherjee, for the wonderful introduction. It is indeed my privilege to present in the FDP. Okay, so in this session, we will see an introduction to the blockchain technology. Okay, so why the blockchain technology is required, and the most important part that we will see in this lecture is what is the application of cryptography towards blockchain technology. Okay, so why cryptography is how cryptography imparts security aspects to the blockchain technology. So first we will take a look at what is a blockchain technology. Okay, so at its core, a blockchain is basically a distributed system that simply records and stores transaction. So more specifically, okay, it is a shared. So it is a ledger you can consider, a ledger or a record. Okay, which is means it is a shared and immutable record of peer-to-peer transactions. Okay, so there is no central intermediate central agency over here. So it is an immutable record of peer-to-peer transactions built from linked transaction blocks and stored in a digital ledger. Okay, so over here the records are linked together, and the records can provide an entire history. Okay, entire history or provenance of an asset. Okay, so what is the provenance? So provenance means, suppose if a transaction has been made in today's date, at a later time in future, okay, any authorized user sitting in the network, he can authorize that whether a valid transaction, whether this transaction that occurred today, okay, whether it was a valid transaction or not, he can verify it. So this is called the provenance of an asset or provenance of a transaction. So a transaction is added to the blockchain only after it has been validated. So once a transaction is performed, it needs to be validated by a set of nodes in the networks with a consensus protocol. So that means, so what does a consensus protocol means? That means the nodes which will participate in this validation process, they need to come to a consensus protocol and agree that that a particular transaction is indeed a valid one. Okay, so this ensures the only version of the truth. Okay, so each record is also encrypted, okay, to provide an extra layer of security. Okay, so initially, okay, so blockchain was initially proposed in the year 1990 and 1991, but it was not taken up seriously. So so at that time, okay, so blockchain was originally intended to be a timestamp digital document. Okay, so it is not possible to backdate them. Okay, that means once a timestamp has been put, that means it is fixed that okay, a particular document or a particular transaction has been produced or validated at this particular time instance. Okay, so nobody can tamper that date. Okay, so however, so from the 1990s to until the year 2008, it went mostly unused. Okay, until it was adopted by a person named Satoshi Nakamoto to create a digital cryptocurrency in the form of a Bitcoin. Okay, so this Bitcoin, it was used for peer-to-peer electronic cash. Okay, that would allow online payments to be sent directly from one party to another without being approved by any financial institution or through any central governing agency. Okay, so that was the benefit. Okay, so the transaction, it consisted of moving specific amounts of Bitcoin from one account to another. Okay, so we will see certain instances over here as well. So typically this blockchain transaction, it uses an established cryptographic technique to allow each participant in a network to interact. So these interactions can be either in the form of storing data, exchanging data, or viewing information. Okay, so without pre-existing trust between the parties. So it is absolutely not necessary that the parties who are communicating in the network, they must be the trusted ones. Even untrusted parties can also participate. Okay, so this cryptographic primitives, okay, such as we will discuss, that is hashing and digital signatures, they impart so much of security that even untrusted parties can also participate in a blockchain network. Okay, so as I said, that a blockchain system, it does not provide any central authority. Instead, the transaction records are saved and distributed across all network participants or the network nodes. Okay, so the interactions with the blockchain, they become known to all participants, and they require verification by the network before new information is added to the ledger. Okay, so that ledger is itself called the blockchain. Okay, so coming to the blockchain basics. So what is a blockchain? So blockchain is basically a peer-to-peer distributed ledger, okay, that is cryptographically secure. So cryptographic security is imparted through cryptographic primitives such as hash functions and digital signatures. It is append only. That means once a transaction is done, okay, that transaction could only be added. Okay, that means the transaction can be added, it cannot be deleted. Means once it is added onto the record, it cannot be removed or it cannot be deleted. Okay, so that's why it's called append only and immutable. That means nobody can change or nobody can tamper with the transaction once it has been put into the record or into the ledger. Okay, and it is updatable. That means the blockchain, that is the record of transactions, it can be updatable only via a consensus or agreement among the peers. Okay, so this is the definition of a blockchain. So now when we come across this, okay, so what is this? So in this case, what we are seeing is that let's say take up the instance of car companies. Okay, so car companies, they make so in India and in many countries, okay, you have these car leasing companies. So what do the car leasing companies do? They issue cars, okay, for hiring. Okay, so the users take the car for hiring for a limited term. Okay, so they hire it for the taxi and other vehicle service purposes. Okay, and then they return it back to the leasing company. So basically, the car companies, they make leasing a vehicle look very easy, but in reality, okay, it is very complicated. Okay, a significant challenge, okay, that is faced by the today's car leasing networks is that even though the physical supply chain is usually integrated, the supporting systems are often fragmented. So over here in this figure, you see that there are. So what are the supporting systems over here? The first is the regulator or the manufacturer. Then you have the dealer. Then you have the leasing company itself, the lessee. That means the person who is hiring a car. And after the car has been used for a certain number of years, say 10 years or 12 years or 14 years, okay, the lessee or the leasing company itself can sell that car to the scrap merchant. So you have a number of parties, okay, or systems associated with it. The first is the regulator or the manufacturer, then the dealer. Okay, for instance, for a typical car company, there are many dealers, okay, who sell the cars. Okay, so the cars are sold to the leasing company. Okay, so basically what happens is that each party within this network, they maintain their own ledger. Okay, so there is no common ledger. Okay, each party within this network, they have their own ledger. Okay, which can take days or weeks to synchronize. That means once a transaction is taking place, that transaction needs to be updated at both the buyer end as well as at the seller end. Okay, so settling a transaction, it may take weeks or days. Okay, so there is a delay that is always involved. So now, by using a shared ledger on a blockchain network, every authorized participant can access, monitor, and analyze the state of the vehicle, okay, regardless of where it is in its life cycle. Okay, whether that car is presently with a manufacturer, that is whether it is in the manufacturing process, or whether that car has come to the dealer, or whether that car is being used by the lessee himself. Okay, so irrespective of the fact, okay, all transactions, okay, will be put onto the blockchain ledger. Okay, and that ledger will be shared among all the participating nodes in the network. Okay, so with blockchain, the network participants can interact as follows. So first, it starts with the regulator. So what does the regulator do? The regulator creates and populates the registration for the new vehicle on the blockchain and transfers the vehicle ownership to the manufacturer. Then the manufacturer adds the make, model, and vehicle identification number to the vehicle template within the parameters allowed by a smart contract. Okay. So now what is a smart contract? It is basically a digital agreement or set of rules that govern a particular transaction. Okay. So the dealer can see the new stock availability. The ownership of the vehicle can be transferred from the manufacturer to the dealership after a smart contract is executed to validate that sale. Now, the leasing company can see the dealer's inventory. Okay, the ownership of the vehicle can be transferred from the dealer to the leasing company after a smart contract is executed to validate the transfer. Then the lessee can see the cars available for lease and complete any form that is required to execute the lease agreement. Then the leasing process, it continues between various lessees. Okay, so there can be various lessees participating on the network and the leasing company until the leasing company is ready to retire that vehicle to the scrap merchant. Okay, so at this point of time, the ownership of the vehicle or the asset is transferred to the scrap merchant, who, according to another smart contract, has permission to dispose of the vehicle. Okay, so these are the entities, okay, who are participating in the blockchain network, and each transaction is guided by a set of rules, which is called the smart contract. Okay, so the conditions for asset transfer or the records of the asset transfer, as shown in the figure, they are being shared among all the entities. Okay, so what does a blockchain do? So the blockchain in this instance, what it is doing, it is facilitating the process of recording transactions and tracking assets in a business network. Okay, so now coming to the asset. So what is an asset? Okay, so an asset can be in two forms. First, a tangible asset. Okay, a tangible asset is something which has its physical form, which you can see, which you can touch, which you can feel. Okay, which you can perceive. Okay, so this asset can be in the form of a house, car, cash, or land. Okay, asset can be also be in the form of an intangible asset, which may not have a physical form, but it has a certain monetary value associated with it. Okay, so that is called an intangible asset. It can be in the form of an intellectual property, patents, copyrights, and branding, and so on and so forth. Okay, so an asset is a physical entity to which you can associate a typical monetary value with it. Okay, so anything having a certain monetary value can be tracked and traded on a blockchain network, and it reduces the risk, and also it cuts down the costs among all the parties who are involved in the network. Okay, so this is the primary job of the blockchain. Okay, that is, it removes the delays, whatever possible delays are there. It removes the risk, means the risk of a transaction. That means there can be different security threats that can be associated with a set of transactions, and also the involved transactions. Okay, means the presence of a central government agency that puts in a large number of costs. Okay, so in the present day transactions, you may see that the banking transactions, for each and every transactions, you need to pay something. Okay, so there are costs involved. Okay, so this blockchain mechanism, what does it do? It removes all such shortcomings in the present day systems. So now here is a typical block diagram of a blockchain transaction. Okay, so what happens in a blockchain system? So somebody or a user, he requests a transaction. So this transaction request. So what is a transaction? A transaction can be in the form of a financial transaction. Okay, for instance, in terms of currencies, it can be the transfer of land record. It can be the transfer of assets. For instance, in the agriculture domain, say vehicles such as tractors. That means transfer of ownership of tractor from one person to another person. This is also a transaction. Okay, so you can consider any transaction over here. So first, a user, he or she requests a transaction. That request is submitted to the request. Transaction is broadcasted to all the user nodes, that is in a peer-to-peer network. All the user nodes in a peer-to-peer network. Okay, it comes. So the user nodes are nothing, but they are the nodes which can perform a certain set of computations over here. Okay, so these nodes, they perform the validation. So validating a transaction means whether means verifying that whether the owner or the seller is indeed the actual owner of that asset or not. The buyer, whether the buyer indeed has enough financial support to perform this buying or not, and so on and so forth. Okay, this means they verify the certain set of rules, that is the smart contracts, before validating a particular transaction. So, and in this validation process, there is a network of nodes that validate the transaction. Okay, using a known set of algorithms. So once a consensus protocol among the validating nodes is performed, the transaction gets verified. Okay, and in this verification process, as the computing nodes, they are putting their computational effort, there is always an incentive associated with all these computing nodes. So okay, so they get monetary gain in terms of cryptocurrencies. So a verified transaction can involve cryptocurrencies, records, transactions, and other information. And once this transaction gets validated, it is put onto the blockchain ledger. So once verified, the transaction is combined with other transactions to create a block of data for the new ledger. So this is the entire blockchain transaction process. Okay, so now the question, why blockchain? Anybody has any question? Okay, so, I would request the audience to please keep their mics on mute.
మీ ఇద్దరిని కంబైన్ చేసిందంట అమ్ములు G&H.
I would request the audience to please mute their mics. Okay, so why blockchain? So what is the need of the blockchain? So it was felt that there is a need for an efficient, cost-effective, reliable, and secure system for conducting and recording the financial transactions. Okay, so there are numerous shortcomings of the present-day transaction system. The first or the most primitive present-day transaction systems, okay, it is the cash. Okay, so cash is useful only in local transactions and in relatively small amounts. Okay, then there is a long time, or there is always a time involved between the transaction and its settlement. Okay, so settlement between the seller and the buyer. Okay, and then there is always a need for third-party validation or the presence of intermediaries that lead to numerous inefficiencies in the system. Okay, and finally, the present-day banking transactions, we have seen that the present-day banking systems, for instance, PNB, Yes Bank, and so on and so forth, they have been subjected to numerous frauds, cyber attacks, and even simple mistake by the bank entities themselves. They add to the cost and complexity of performing their business. And hence, as a result, it exposes all the participants in the network. Means the private information, the private credentials of the users, okay, they get leaked. Okay, and okay, so they are always at risk. And if a central bank such as and if a central system such as a bank, if gets compromised, that can be very detrimental to the entire set of the users. Okay, so basically, in addition, for instance, certain industries, for instance, shipping industry, there is limited transparency, and there is always an inconsistent information that hinder the efficient movement of goods from one place to another place. Okay, and this has become very much important as the transaction volumes, okay, say be it in the form of a tangible asset or in intangible asset, the transaction volumes, they have been growing exponentially. Okay, and it magnifies the complexities. So that's why this magnifies the essence of the blockchain in the present day transaction systems. Okay, so these are the certain features that is building the trust with blockchain. So the blockchain, what does it do? It enhances the trust across a business network. It is not that you cannot trust those whom you conduct business with. Okay, it's that you don't need to when you're operating in a blockchain network. That means when you're operating in a blockchain network, you need not worry about whether a particular party is whether he is a trusted party or whether he is an untrusted party. So the blockchain is particularly valuable at increasing the level of trust among the network participants. Why? Because it provides a cryptographic proof over a set of transactions, because the transactions, once they are put into the ledger, they cannot be tampered, and they are signed by relevant counterparties. Okay, so that means if any corruption happens, that will be readily apparent to all the users in the network. Okay, so this self-policing can mitigate the need to depend on any central governing agencies or your government safeguards, okay, and sanctions to monitor and control the flow of business transactions. So the first feature that we see over here is that in blockchain, that the system, it is distributed and it is sustainable. That means the ledger is shared, updated with every transaction, and it is selectively replicated among the participants in almost near real time. So because it is not owned or controlled by any single organization, the blockchain performs continued existence that is not dependent on any single individual entity. Okay. Moreover, the transactions are secure, private, and indelible. That is, the permissions and cryptography primitives, they prevent unauthorized access to the network and hence ensure that the participants are indeed who they claim to be. That means authentication, user authentication is always performed. So confidentiality is usually maintained through cryptographic techniques such as the encryption or decryption mechanisms, and there can be different data partitioning techniques to give the participants only limited or selective visibility to the ledger. Means there can be certain important transactions which you would not want to make them visible to a certain group of users. Okay, so you can make certain data partitioning techniques as well over here. So both transactions and identity of transacting parties can be masked. Okay, so after conditions are agreed to, the participants cannot tamper with a record of the transaction. So errors can be reversed only with new transactions. Okay, so moreover, the transactions are transparent and auditable, and they are usually consensus based and transactional, as I told. Okay, so all relevant network participants must agree that a transaction is valid. So this is achieved through the use of consensus algorithms. Okay, so each blockchain network can establish the conditions under which a transaction or an asset exchange can occur. Okay, and finally, it can be orchestrated and it is flexible. That means as the business rules and the smart contracts, that is the rules which based on which the execution of the transactions are performed, okay, they can be built into the platform. Okay, so the blockchain business networks can evolve as they mature to support end-to-end business processes and that can support wide range of activities. Okay, so any questions until this point? Any questions?
Sir, can you give a quick recap about scrap merchant, sir? How the blockchain technology is used in scrap merchant?
So the scrap merchants, they keep a record of how the transactions. Suppose there is a vehicle that has been used for 10 to 12 years. They keep a track of all the vehicles that a particular vehicles have been in use. Okay, for how many years and how is it proceeding towards scrapping. Okay, so that so that enables them to have a plan. Okay, so as to how many vehicles would be coming for the scrapping and how they can dispose of. So they can get an idea on this. Okay, any more questions?
Hello, sir.
Yeah.
Sir, in the consensus base, where the validation agreement will be the main protocol, right? Everybody has to agree the transaction.
Right.
So in a network, what would be the time capacity complexity that would arise in this?
Can I take can I take a break of 2 minutes, please? Hello.
Hello.
Hello. Can I take a break of 2 minutes?
Okay, sir. Okay, no issue.
Hello. My camera is giving a problem. Hello. Can I rejoin? Hello. Hello.
Hello, sir, you're audible.
I'm audible. Okay. So is my slide visible?
Yes, sir.
Yes, sir.
Okay. 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 So yes. Can you please continue the question? What was the question?
Yes. Yes, sir. In a consensus-based transaction, each node has to agree, each block has to agree with the transaction, right? Every transaction which is immutable, then
Right.
in reality, for a banking transaction, how it would be like for 100 people of taking an example of any bank, 100 to 500, more than thousands of customers will be there. How it could be really applicable? Can you give us the in real knowledge about this consensus-based transaction?
So basically, in a consensus-based transaction, there is a set of computing nodes. They are called the miners. Okay, so they need to solve a cryptographic puzzle. Okay, so that cryptographic puzzle, so that is added along with a transaction. So a transaction's verification has to be done. That means the user's accounts. Okay, that whether means they perform to all sorts of verification that whether a particular asset is indeed means whether the seller is indeed the original owner of that asset, whether the buyer has has sufficient balance or not. Okay, and along with it, so these are merged to along with a certain cryptographic puzzle. Okay, so the miners, they need to solve a set of cryptographic puzzle. Okay, so the miner who first solves that puzzle, okay, he provides that solution to all the miners. Okay, then the miners, they verify, okay, that whether this solving is a correct solution or not. Okay, this verification takes a very less amount of time and energy, but solving that puzzle is indeed very critical. Okay,
Yes, sir.
so this,
That's why I'm asking, this consensus provided by every people
yeah,
or a minor. It would take a time limit of maximum or average time limit it may take, right? For each
no,
and
for
every transaction.
no, for verification, no, for verification, it takes a very small amount of time. But solving that cryptographic puzzle, okay, that is
Yes.
itself challenging. That means that takes a
Yes,
significant
that
amount
is
of
it.
time.
Then how we could apply the blockchain technology in banking domain, sir? Is it really applicable in real time, in real sense?
Yeah, in present day world, this banking, it is a real challenge. Okay, miss
Yes,
porting all the banking transactions can be a real challenge, because there is a huge amount of energy involved, because solving the cryptographic
sir.
puzzles, you need a large computation energy. So present day, so that's why the present day means many blockchain technologies are, in terms of cryptocurrencies, they are evolving. For instance, Dogecoin or Ethereum and so on and so forth. So they provide optimizations in one or the other aspects. Means there cannot be a single system which can solve all the applications or all the challenges.
So in this sense, if you take up this, definitely it would be a real challenge to us in implementing this in banking system.
Yeah.
Though it is very strong as functions as cryptographic algorithms involved, it
Right.
would take a challenging
Right.
issue. So
Right.
can you just brief us what are the other challenging issues that we could take up in solving the issues in blockchain for the real application?
Right. So basically, in this lecture, we are focusing on how the cryptographic primitives, they impart all the security challenges. Okay. So first is the hash function, and then we'll take up the aspect of digital signatures. So these cryptographic primitives, okay, they ensure that that a certain set of security challenges that can be thwarted. Okay.
And as per my knowledge, the first incentive cryptocurrency was Bitcoin, and then it comes with the Ethereum blockchain,
right.
where these two are the leading cryptocurrencies, which was initiated by Satoshi Nakamoto in 2009. What he has deployed with the Bitcoin, it is having the most dominant cryptocurrency in the world now.
Right.
Though they are having a strong cryptographic algorithms which couldn't be broken, can we adopt such kind of cryptocurrencies or such kind of blockchain technologies to our system? Can you, after this session, can you elaborate on that part so that we can have certain thirst areas in the blockchain where we could go deep dive into the research process? Can you give a limelight on that at the end of the session?
Yeah. I will try to put focus on that aspect. So the first aspect is that okay. So thank you. So the first aspect in this that we'll take a look into the cryptographic background. So why cryptography is required? So cryptography was initially proposed, okay, or cryptography. The domain of cryptography, or the cryptography, or the main application that cryptography found, was in the domain of communication and in computation. So in communication, it imparted certain aspects. That is, first is the confidentiality. So what is confidentiality? So suppose there is a message that is being sent by user A to user B. So there is a sender and the receiver. Okay, and both the sender and the receiver, okay, they want to ensure that the message that is being exchanged, that message should be known only between the sender and the receiver, and to nobody else. Okay, so suppose there is an eavesdropper who is snooping on the insecure communication channel. Okay, so to such an party, okay, the message that has been sent, that should look completely unintelligible. That means any eavesdropper who is snooping on that communication line, that message should be unintelligible. That means looking at the encryption or the encrypted ciphertext, the user, the eavesdropper, he doesn't get any information about the original message. So that is called the confidentiality. The next aspect is that of data integrity. So what does data integrity say? Data integrity means that if there is any tampering with the data by any eavesdropper, okay, so that tampering can be easily tracked. Okay, so this can be done. So this tracking can be done both by the sender as well as the receiver. Okay, so there usually occurs a communication of the messages. So data integrity can be incorporated through a set of cryptographic primitives, and then you can have both the source authentication as well as the data authentication. That means the sender is indeed the person who is sending the data. That means the receiver should be assured that I am getting the data from the intended sender only, and nobody on his behalf is sending that data. So that sort of authentication can also be imparted through these cryptographic primitives. Okay. So moreover, in the present day world, we have seen that there have been computations that are performed on the cloud. So data is stored on the cloud, and computations are performed on the data. So here comes two aspects of security. First is the data in storage, and then the data that you are putting to computation. So you need to secure the data itself as well as the programs that are performing the operations or which they are the programs that are processing that data. So the security of these aspects are also put to computation. Okay, so security of these aspects are also ensured by the set of cryptographic primitives. Okay, so and there is another application of cryptography that is towards complexity theory, wherein cryptographic primitives such as pseudo-randomness that are interactive and probabilistic proof verification. Okay, so all these things have come into the last 2 decades. Okay, so that is the probabilistic proof verification. Okay, so first we'll take a look at how the cryptography has improved over the past few years. So first in the 1970s, the public key encryption was proposed. Okay, wherein the sending of secret messages without ever meeting. Okay, so that means the sender and the receiver. Okay, they could send messages without sharing anything. That means over here it is an asymmetric encryption. That means the sending and the receiving can be performed with 2 different key values. Then you have the digital signatures. Okay, that is signing the contracts remotely. That means the sender can sign on a set of documents, and the receiver can verify that this is the signature. Okay, that has been indeed that has been signed by the original sender. Okay, so this is the mechanism of digital signatures. Then you have the pseudo-random number generation. Pseudo-random number generation modules. They are very important for the key generation purposes, so that any attacker, okay, for that attacker, okay, that any encrypted message that has been sent, that should be completely unintelligible to him. That means it should be indistinguishable from random. Then you have the zero knowledge proofs. For instance, if you are performing a particular banking transactions, or if you want to show that you have indeed an X amount of money in your account that is larger than Y amount, okay, so without revealing the values X and Y, okay, you want to show a proof that indeed you have sufficient amount of money in your account to perform a particular transaction. So this can be done by a system called the zero knowledge proofs. That means you are not imparting any knowledge to the verifier, okay, but you are proving that indeed you have sufficient money in your account to perform a particular transaction. Then the two-party secure computation that came up, wherein oblivious transfer. That means once a message or once a transaction is being transferred, okay, so that can be done without letting the receiver know what is the actual amount of money. Okay, so this is called the oblivious transfer. And then you have the multi-party secret protocols. That means this is a set of communication protocols which involves both a set of trusted as well as a set of untrusted parties. Okay, so Byzantine agreement, okay, is an example of this multi-party secure protocols. So coming to the public key crypto system. So this public key crypto system is indeed important from the blockchain's perspective. So over here, a party, okay, or all the parties, each party that is participating in the network, he has a pair of keys, that is a public key and a private key. So so both these keys are generated by a key generation algorithm. Okay, so the public key of the user that is known to all other users in the network, but the secret key is known only to that respective user. Okay, so this is called the private key, which is known to that user itself, and the public key of that user that is known to all other users. So the public key is widely disseminated, but the private key is kept secret and it is shared with nobody. Okay, so the secret key is used by the party who generated it. Okay, but the public key is used by everybody else. So that's why it's called an asymmetric key. Okay, so the security must hold even if the attacker knows the public key, because it is assumed that the public key is already existing in the public database. Hence, any user, okay, including the attacker, has access to the public key. Okay, so this is how the public key distribution is being done. Okay, so corresponding to each user, a public key and a secret key is generated by the key generation algorithm. The public key of the user is put to the public database through which all other users can access or gain access to, and the secret key is kept by the users, by that user herself. Okay. Otherwise, instead of putting the public key to the database, the sender can share. Okay, the user can share his or her public key to the other nodes in the network. Okay, so only public keys are being shared, whereas the secret key or the private key, that is being kept secret. Okay, so this usually addresses the drawbacks of private key encryption scheme. So in the private key encryption scheme, what the general notion is that the same key is being shared between the sender and the receiver. So how the same key can be shared between the sender and the receiver? So this is indeed a very big challenge. So this sharing of the secret key is not required in case of public key encryption scheme. So the key distribution is much easier in case of a public key encryption scheme. Okay, and also the key management in a large system of users. Okay, that is also easier, because a user needs to store his or her own private key. Okay, and the public key needs to be shared in between n-1 users. Okay, that means the user, a particular user, he needs to store his own private key as well as n-1 public keys. Okay, so these public keys can be stored in a central directory. Okay, so this can be applicable in a wide range of open systems. So even parties who have no prior relationship can find each other's public keys and use them. Okay, so then the question comes, why study the private key? Because the private key is much more computationally faster, it is much more easier, and it consumes lesser resources. So the private key cryptography is more suitable for certain applications, for instance, disk encryption. Okay, so and also it is roughly 2 to 3 means public key encryption, or if you use any public key crypto primitive, it will be roughly 2 to 3 orders magnitude slower than the private key encryption. Okay, so if private key encryption is an option, that means if it is feasible, then we usually go for private key encryption. Otherwise, we go for the public key encryption. So in this case, so in public key encryption, how is it accomplished? The first is, so suppose there is a sender. So what does the sender do? Sender first accesses the recipient's public key from the central directory. Okay, so he accesses the public key, and then he encrypts that the message that he wants to send with this public key, that is PK. That is PK of the recipient or the PK of the receiver. Okay, so this is a randomized process. So this generates a ciphertext, and then this user, he sends the ciphertext to the recipient. Okay, so now the recipient, as it is assumed that the secret key is only there with the recipient, she can decrypt that ciphertext or that encrypted message with her own secret key to get back the original message. So the security of this public key encryption scheme is guaranteed under the assumption that the recipient only has as the recipient himself or herself stores the secret key with herself. Okay, so this secret key is not shared with anybody else. So under this model, this public key encryption scheme, okay, transactions or any communication involving public key encryption scheme, okay, that remains secure. So a public key encryption scheme, it is composed of 3 probabilistic polynomial time algorithm. The first is the key generation algorithm, okay, which takes in the secret parameter, that is how many bits of the key that it needs to generate. Then through a randomized algorithm, okay, it generates a pair of keys, that is the public key and the secret key. Then the encryption algorithm, it takes in the public key of the recipient, okay, and it encrypts the message M and outputs the ciphertext C. This ciphertext C is sent on the insecure communication channel, which is received by the decryption algorithm at the recipient's end. And this decryption algorithm, it takes in the secret key of the receiver and it decrypts the ciphertext and outputs either a message M or an error. Okay, that means it can also perform an authentication. If the authentication fails, then it can flag an error. So this is the proof of correctness. That means for all messages and for all possible public key and the secret key values that are output by the, that means for all possible pairs of your public key and secret key that is output by the key generation algorithm, okay, and a message when it is encrypted by the public key, and then again if it is decrypted by the secret key, you must get the message back. So this is the proof of correctness. Okay, so this should be satisfied by any public key encryption scheme that you are considering for any application, whether it is blockchain purpose or whether it is for any security purpose. So these are the so this proof of correctness must be established. Okay, then you have the chosen plaintext attack security. So this is basically this security is towards message indistinguishability. So in this case, what happens is that suppose there is an adversary A, okay, who attacks an encryption scheme pi. So this encryption scheme pi comprises of these 3 algorithms, that is the key generation algorithm, the encryption algorithm, and the decryption algorithm. Okay, so this adversary, okay, he runs a chosen plaintext attack. So what does it do? First, the key generation algorithm, it generates a pair of public key and the secret key. Then this public key is given to the adversary A, okay, who outputs 2 messages, M0 and M1, which are of the same length. Okay, so now he chooses a uniform B. Okay, so now the user, okay, he chooses a uniform B, that is a value B is chosen uniformly at random, that is either it can be a 0 or 1. So you can consider the output is taken from a coin tossing experiment. Okay, so the user, he chooses a message, either it can be M0 or M1. So B refers to the suffix 0 or 1. So if it is if B equal to 0, then he encrypts M0. If B is equal to 1, then he encrypts M1. So the user, what does he do? He randomly chooses one of the messages, he encrypts it with the public key and gives the ciphertext C to the adversary. So now, if this is repeated for a number of message pairs, okay, and from those message pairs, okay, if the adversary is able to output a guess B dash, okay, and the experiment evaluates to 1 if B dash equal to B. That means if the adversary is able to correctly predict that whether M0 was encrypted or whether M1 was predicted, and if he is successful in predicting that, then this attack experiment is successful. That means the security is not valid in this case. If it evaluates to 1, that means the security is not guaranteed. So any public key encryption scheme that you want to consider, it should pass this CPA security. That means this game should fail. That means this evaluation should give you 0. Okay, so this should give you 1 or 0 with probability exactly half. That means it would be completely unpredictable whether an adversary, a computationally bounded adversary, whether he succeeds, okay, in mounting this attack. Okay, so this is the CPA security definition. That means the probability of succeeding in this game should be as close to half as possible. Okay, so this is the definition of a secured public key encryption scheme. Okay, so now in this case, the encryption can be done. So now this public key encryption scheme, okay, this can be used to share the secret key, okay, that is used in in the private key encryption scheme as well. For instance, what happens over here is that, let's say, suppose this ENC dash. Okay, so this encryption is basically the private key encryption scheme, okay, which uses a secret key K. So now the user or the sender, what he does is that he takes in this secret key K, he uses this secret key K to perform the encryption on the original message, and he generates the ciphertext and sends this ciphertext to the sender. And along with this ciphertext, what he does is that he encrypts this K, the secret key K, with the recipient's public key. Okay, so he encrypts this K with the recipient's public key, and he sends this encapsulated key to the receiver. Then the receiver, what does he do? He then decrypts this K using his own secret key. Okay, as corresponding to this public key, there will be a secret key to that recipient, and using that secret key, he recovers back this key. Okay, he decrypts back this key and then uses this key to decrypt to perform the decryption and get this original message back. Okay, so decryption can be done in the obvious way. So this is how the public key encryption and private key encryption can be used in tandem. Okay, to thwart a wide range of attacks that can be thought of. Okay, so I'm not going into much details. So this is an instance of an authentication. So over here, so there is this person Bob. What does he do? Suppose this is a kind of a signature scheme. So in this case, suppose Bob is performing a financial transaction with this person Lisa. So he pays a $10 note or a $10 currency to Lisa. So what he does is that Bob signs with his own private key. Okay, so when it is signed by the Bob's own private key, so that means this is a valid signature, and the validity of this signature must be established by the recipient. So how does the recipient validates this signature? Okay, she validates this signature by using the Bob's public key. So this authentication is being done by the Bob's public key, and once this authentication comes to be true, then Lisa becomes assured that this message indeed came from Bob. That means Bob has indeed paid $10 to me. Okay, so this is kind of an authentication. Okay, so this signing can be done by the private key and the validation can be done by the public key. So this is another application of the public key encryption scheme that can be used in the blockchain system. Okay, then you have then you can have the message privacy. So using so in the message privacy, what happens is that Lisa, after she gains this validation, okay, that Bob has sent her this $10 amount, she sends an acknowledgement to Bob back. So sending the acknowledgement, that means she needs to encrypt that acknowledgement message. So here is my link. That means she gives the link from where Bob can download that receipt. So what does she do? She again encrypts this message with the Bob's public key. So now this is an example of the message privacy. Okay, so once this message is encrypted by the Bob's public key, only Bob can decrypt it back because this decryption happens with the Bob's private key. Okay, so this this gives a link. So after decryption, Bob's find a link to Lisa's resource file. So from wherein he can download the receipt or he can download the corresponding resource. For instance, he can download the ebook or he can download the receipt. Okay, so he can decrypt this message using his own private key. So this public key encryption scheme can be used for authentication as well as for encryption. So that's why this public key encryption scheme are used for any blockchain transactions. Okay, for establishing the authentication of the sender as well as sending an encrypted message. Okay, so in addition to this, we have a set of cryptographic primitives that is called the hash function. So any questions at this point? Anybody?
Hello.
Any questions?
Yes, sir. Actually, I have one question myself, Mukherjee.
Yeah, yeah.
I have one question regarding the nonce value. So that nonce value is decided by whom? It's decided by miners only, or it has some rules?
Which one? The nonce?
Nonce, yes.
Yeah, I will come to that.
Okay.
Okay. So in this case, in the hash functions, okay, so this is a typical transaction that is happening in a blockchain transaction, wherein the signature to a particular transaction is being done by the owner's private key, and the verification can be done by the owner's public key. Okay, so in this case, a hashing transaction is being done. That is along with the previous transaction, the owner's public key. So the owner's public key owner's public key is used as the owner's ID. Okay, so both these components are taken and hashed along with it. Okay, and this hash has a certain set of properties that it needs to fulfill. Okay, and the output of the hash is basically a fixed bit output, so which is easier to sign. So the owner puts the signature to this hash output with his own private key, and this can be validated by the buyer. By the recipient of this financial transaction. Okay, so this is how the currency transactions are performed in a blockchain. So typically, what is a blockchain? So typically, what is a hash function? So basically, a cryptographic hash function. Okay, it is a mathematical function. Okay, which satisfies these three properties. That means, first is it can take a string of any size as input. Okay, so it takes a string of any size as input, but it always gives a fixed size output. Okay, so the output can be of 256 bits, and the third criteria is that as it can take in a string of any size, that means it can be an infinitesimally large string as well. Okay, and from that for that large input string, it should create a hash. Okay, which is a fixed size output. Say the present day hash functions, for instance, SHA-256. It creates an output of 256 bits, and it has to be efficiently computable. Why? Because the input can be of a very large size. So computing, that means performing operation on a very large size input, that has to be finished within a polynomial runtime. Okay, so so that's why it should be efficiently computable. Okay, so intuitively this means that for a given input string, you can figure out what the output of the hash function is in a reasonable amount of time. So more technically, computing the hash of an n-bit string should have a running time of big O of n. In addition, it should guarantee a set of security properties. Okay, hash function, when used for blockchain purposes, it should satisfy a certain set of properties. That is, the first is that it has to be deterministic. Deterministic means suppose if you give an input, okay, say 1000 times, then for all those respective 1000 times, the corresponding output should be the same. That means if you keep the input fixed, your output should not change. Okay, so this is absolutely necessary to guarantee the reliability of that system. Okay, if you're not changing the input, your output should not vary. If your output varies or changes, that means the system that you are building, the secure system that you are building, that is not reliable. Okay, so that's why this hash function should be deterministic. That means no matter how many times you give a particular input to a hash function, you should always get the same result. Okay, so what happens if this property is not present? If this property is not present, then the system will not be reliable. The second property is that it should have the collision resistance property. Okay, that means over here in a hash function, a collision occurs when two distinct inputs, they produce the same output. Okay, for instance, a hash function is collision resistant if nobody can find a collision. Okay, so what is the definition of collision resistant? A collision resistance means a hash function is collision resistant if it is infeasible to find two different values or two unique values x and y, okay, for which the corresponding hash values would be the same. Okay, indeed, it can occur that that for two different values, that for two different inputs, the hash values can be same. Okay, why is it so? Okay, why is it so? Can anybody answer? why collisions will always be there for a hash function? See, as I said, that when you go to the definition of hash function, it can take string of any size as input. That means the input domain is a very large domain, whereas the output range, okay, it is a finite size. That means it is the range. The output range is typically, if it is 256 bits, then the output range is 2 raised to the power of 256. Okay, so that means the input domain is a very large domain, whereas the output range is a small range. That means if you try to define a function, so basically hash function is basically it maps from this set X to this set Y. So mapping from a large set to a small set, okay, then by the pigeonhole principle, okay, it means there will always occur two different input values which will map to the same output value. That means this is an instance of a collision. That means for two different input values, they are mapping to the same value. Okay, so from the pigeonhole principle, okay, so hash functions, collisions will always be there, but this collision resistance is defined in terms of the computational efficiency. That means nobody, okay, should be able to find a collision in a computationally feasible time. That means in polynomial time. Okay, so collisions, so that's why it's called, the collisions are infeasible but not impossible. Okay, so can anyone find them? Okay, so to find the collision, what one has to do is that one has to iterate over all possible values of the output. Okay, so there are 256 bits. That means the number of possible outputs is 2 raised to the power of 256. Okay, so he can randomly choose. Okay, so he can iterate over all possible output bit values and find whether a collision exists or not. Okay, but to mount a brute force attack on this entire sample space, that is 2 raised to the power of 256, that is not possible in one's lifetime. That means finding such a brute force or finding a collision is not computationally feasible. Okay, it may take billions of years to find a single computation if the hash function is defined in this way. Okay, and also it depends upon the definition of the hash function as well. If it is a strong cryptographic hash function, in that case also, even if the collisions exist, it will be highly improbable to find such collisions over here. Okay, so there is another way that is called the birthday paradox. So the birthday paradox is a mathematical tool that guides you that you don't need to brute force over the entire sample space of 2 raised to the power 256. So the birthday paradox, what does it say? It says that instead of 2 raised to the power of 256, even if you iterate it over a much smaller sample space, that is square root of the brute force search space, that is 2 raised to the power of 130. Okay, if you consider 2 raised to the power of 130 randomly chosen input, then even then the attacker can get a 19.8% chance to find a collision point. Okay, so that means birthday paradox, it gives a tool to the attacker to find a collision for the cryptographic hash function. Okay, so this is what the birthday paradox is. But still, this sample space, that is brute forcing on this sample space, that is 2 raised to the power of 130, this is also a very large sample space. Okay, hence to attain this probability, this is also computationally infeasible in a person's lifetime. Okay, so this works no matter what your hash function is. Okay, so this birthday paradox is valid irrespective of how strong your cryptographic hash function is. But the thing is that it takes too long to matter. That means it is computationally infeasible. Okay, so is there a faster way to find collisions? It depends upon how the cryptographic hash function is defined. Okay, so there are certain hash functions, okay, for which the collisions are much easier to find. Okay, but the most strongest point is that until now there has been no hash function which has been proven to be collision free in this case. Okay, so for cryptographically strong hash function, if we know that the hashes of two messages, they are same, okay, then it is very safe to assume that those two messages are the same itself. Okay, so a typical application of a hash function, of applying a strong hash function is as follows. Okay, that means, say, suppose if you have a large video file or a large message file, say of the order of GBs, okay, what you can do is that you can store that large message file or the video file into a cryptographic locker, say a digilocker. Okay, and when you require it, you can recover it back. Okay, but you need to ensure that the file that you have recovered, that is indeed the original file or not. So for that, what you will do, before storing that large message file to the digilocker, what you will do, you will pass on that large file through a hash function. You will store the hash. Okay, so as the hash output is a very small output, that is a finite output. That means it is of 256 bits. Then that means instead of storing the large video file, you are storing only its hash. So when you recover that large video file from the digilocker, you can again pass on that large video file through the hash function, and then you can compare the corresponding hash outputs of the computed and the stored hashes. If they match, then you can be ensured that the video file has not been tampered with. So this is an instance of data integrity. Okay, so it is useful because the hash size is usually finite, that is of the order of 256 bits. That means you need to compare only these 256 bits instead of comparing the GBs of data. Okay, so this is an important application of a cryptographically strong hash function. The next property that the hash function in typical blockchain applications to satisfy is that it should be a pre-image resistant. That means given the hash of an input, okay, an attacker or an adversary should not be able to find out what is the corresponding input. Okay, that means given access to the hash of a message, okay, an attacker should not be able to find out what was the corresponding message. So this is called the pre-image resistance. Okay, so but now over here there is a caveat, that is the input sample space that should not be too small. For instance, so suppose if you perform a particular computation and what computation you perform, okay, so suppose and what computation you perform, that depends upon the output of a hash function. So suppose there is an adversary, okay, who has an access to the output of that computation. So now from that output of that computation, okay, he can if he can reverse engineer and find what is the input of that computation algorithm, and from that input of the computation, and if that input of the computation algorithm is dependent upon the hash output, that means the adversary has access to the hash output, and as the sample space is very small, say it is either heads or tails, then he can identify what was the original input, that is whether it is heads or whether it is tails. So the experiments that is considered, it should not have a small sample space. Okay, that is X should be chosen, that is the input should be chosen from a large set of values, and that must be spread out. Okay, that means the probability of choosing a particular message value, that should be infinitesimally small. Okay, so that is what is known by the spread out definition. Okay, so for an adversary, it should not be possible to try all possible values of X. That means the input sample space should be as large as possible. That means the adversary should not be able to mount a brute force attack on the entire over the entire search space, and there should not be a condition that there are certain values of X which are highly likely, or in other words, the probability of selecting a particular or any message value, that should be infinitesimally small. Okay, so over here we see that what does this pre-image resistance reflect to in terms of the blockchain application. Okay, so over here, this is called this property of hiding, or this property of pre-image resistance, it translates to the property of hiding. Okay, so a hash function h, okay, it exhibits a hiding property when a secret value, say suppose r, okay, is chosen from a probability distribution that has a high mean entropy. Then given the access to the hash of this secret value or this random value appended with this X, okay, if the adversary is given access to the hash output, then it should be infeasible to find X. Okay, so R should be, if R is chosen from a probability distribution that has a high mean entropy. High mean entropy means, that means you are selecting a value from a set whose probability distribution, okay, that is the probability of selecting any particular value should be infinitesimally small. That is, the distribution is very spread out so that no particular value is chosen with more than negligible probability. Okay, so for a hash function, any particular string R is chosen with a probability of 1 by 2 raised to the power of 256, which is in fact a very negligible value. So this R that you are selecting, so the secret value R that you are saying, this translates to the nonce in the blockchain parameter. Okay, so this application of hiding property, you can reflect this application of hiding property towards a commitment scheme. So now what is a commitment scheme? So a commitment scheme is as follows. For instance, so suppose you have an envelope. Okay, suppose you committed 1,000 rupees. Okay, so suppose you committed 1,000 rupees to an envelope. That means, so suppose you have put a 100 rupees note within an envelope, and you have put that, and you have sealed that envelope. Okay, and that envelope you have put it on the table, or you have put it into a locker, and at a later point of time, okay, say some person takes out that envelope, okay, and then at that point you have claimed that, okay, that you have put 1,000 rupees in that envelope. So then that person, he validates that whether there are 1,000 rupees in that envelope or not. So this is called the commitment scheme. That means the person who is storing that money, he commits to a particular amount of money, and then at a later point of time, okay, that is verified. Okay, so here there are two activities that are happening. That is, first is sealing a value in an envelope, and the other is opening the envelope later. Okay, so first you commit to a value, and then you reveal that value later. So here is this thing. So here the message is basically the amount of money that you are committing, and you are committing this message by using the key. So the key is basically the sealing of that envelope. Okay, how you are putting the glue to the envelope. Okay, so that is the key. Okay, and then once you have put that money in that envelope, that becomes your COM, and at a later point of time, that COM or the amount of money that is verified. Okay, so at that point of time, you claim that you had put 1,000 rupees in that envelope. You then break that seal of that envelope. Okay, and then you verify that whether the claimed amount is indeed the amount that is there within the envelope or not. So there are two functions. First is the commit function, that means committing a particular amount of money in that envelope, and then opening that envelope later to verify the commitment that you have given. Okay, so here there are two. So this is the property of hiding. That means you are hiding that amount of money within that envelope. That means over here there are two security properties that needs to be proven. That is, first is the hiding. That means given COM, or in other words, that means given COM means by observing the envelope, it should be infeasible to find the message. That means by observing the envelope, one should not be able to find out how much amount of money you have put in the envelope. That means nobody else should be able to tell how much amount of money is there within the envelope just by looking at the envelope. So this is called the hiding property. And the other security property that it should satisfy is the binding property. So what is binding? So suppose at this point of time, so suppose I am putting a 1,000 rupees note within that envelope. At a later point of time, at the time of verification, okay, you should not be able to claim that, hey, I had not put 1,000 rupees earlier, I had put 10,000 rupees. Okay, and for that 10,000 rupees, okay, that verify scheme should not succeed. So this is called binding. That means for two different message values, that means for two different amounts of money, the commit scheme, okay, should not give you the same output. That means the envelope, the state of the envelope should not be the same for two different message values. Okay, corresponding to the nonce. So nonce is what? Nonce is basically the secret, okay, that is chosen from a sample space which has a very high mean entropy. That means probability or the likelihood of choosing a particular or any value from that sample space should be infinitesimally small or negligibly small. Okay, so that is the property of the nonce. Okay, so this nonce, so basically this nonce is basically that is how you are gluing or putting a seal to that envelope and then opening that envelope later. Okay, so for two different message values or for two different financial monetary values, okay, this commit scheme should not give you the same output. So these are the two properties which a cryptographic hash function in a typical blockchain transaction should satisfy. The first is the hiding, the second is the binding. Okay, so every time you commit to a value, it is important that you choose a new random value called the nonce. Okay, so that is this nonce. So that is this nonce over here. Okay, so this nonce also defines this property, that is the hiding and the binding properties. Okay, that is for two different messages. Okay, the verify and commit should not give you the true value. Okay, so for a cryptographic hash function, so once suppose this message, so this is a fixed message that a user has chosen, so it can be 1,000 rupees, it can be 10,000 rupees, and so on and so forth. To this message, a random nonce is chosen from a large sample space. Okay, and from that large sample space, the probability of selecting a particular value or any value from that sample space should be infinitesimally small. Okay, so the nonce should be chosen from that sample space. Okay, so it is a random 256 values. Okay, so given access to this hash value, okay, nobody should be able to predict what was the nonce, or nobody should be able to tell what was the nonce value. Okay, and this is the verify scheme. Okay, and hence the corresponding hiding and the binding property. So the binding gives you the collision resistant property, that is for two different financial or the monetary values, the hash should not be the same. Okay, so now next comes the most important property of a cryptographic hash function to be employed in a typical blockchain transaction, that is called the puzzle friendliness. So a hash function h, okay, so this is not required for the cryptographic hash function for other applications. This is specifically required with respect to a blockchain application. Okay, so what does this define? So this defines that a hash h is puzzle friendly if for every possible n-bit output value y, okay, so this y is supposed to be an n-bit value. If k, here k is actually the nonce that you are talking about. So if k is chosen from a distribution with a very high mean entropy, then it is infeasible to find x. Okay, such that the hash of k appended with x is the output value y itself. Okay, and this finding this x should not be possible in a time significantly less than 2 raised to the power of n. That means it should not be possible to find x in polynomial time. Okay, that means it should not be feasible to find in a means finding this x by getting access to the y. Okay, should be polynomial time infeasible. So here is the definition of the cryptographic search puzzle that the miners try to solve. The first is a hash function is given h, then a value ID or a puzzle ID is given, that is the ID that is chosen from a high mean entropy distribution, and a target set y is given. Okay, so now here k is chosen, k or the ID is chosen from a high mean entropy distribution. The hash function is known to the miner. Also, the miner is provided with the value y. Either he is provided with a value y, or either he is provided with a set of values y. So now, initially, when the blockchain was initially proposed, so for instance, for the Bitcoin transaction, this set y was a very large set. So if this set y is a very large set, then finding a collision, that means finding an x such that the hash of the ID appended with this x gives you a value from this set. So if this set y is a very large set, then the probability of finding a collision, that is probability of finding an x, is very easy. So now with over the past decade, as the computational power of the miners have increased, this set y has shrunk over the period of time. So the hardest possible puzzle instance is that if this set y is a singleton set. That means if this collision has to be found for a particular value, then this puzzle becomes the hardest instance. Okay, so if this target set y is a singleton set, then this becomes the hardest puzzle instance for this problem. Okay, so this hash function should satisfy this puzzle friendliness property. That means it should be harder for a miner to find a typical X. So that's why a large amount of energy is required to find the value of X, okay, such that K appended with X, and when it is hashed, okay, that hash value should belong to the set Y. So if the cardinality of the set is a very small value, then this cryptographic puzzle becomes very, very hard. Okay, so then in that case, the adversaries have no option, but the adversaries or the miners have no option but to perform a brute force attack. Okay, and then the last property that guarantees the immutability property. Okay, so what does it say? It says that if you change the input to the hash function even by a very small amount, okay, then the hash output should change randomly, absolutely random. So this property, this is called the avalanche criteria. It guarantees the immutability property of the blockchain. Okay, so immutability property is required to track that whether any record has been tampered with it, or not. So the hash function, it guarantees this. With this avalanche criteria, it guarantees the immutability property of the blockchain. Okay, so this is the standard hash function that is used in the present system. So this is the SHA-256. It uses a compression function. So as I defined, that a hash function can take an input message of a very large size. Okay, so then this SHA-256, what does it does is it partitions the message in blocks or chunks of 512 bits. So suppose this message is partitioned into n blocks, then there is a compression function that is defined. So this compression function takes in an initialization vector of 256 bits, and it takes in the first message block of 512 bit. This compression function then outputs a 256 bit output. Then this output is again passed along with the next message block to the same compression function, and it is done for n number of message blocks. And the output of the last compression function is the fixed size hash output, that is of 256 bits. So the security of the SHA-256, it basically depends upon the security of the compression function. So that's why this is called the Merkle-Dampert construction. The Merkle-Dampert construction, it guarantees that the security of the entire hash function, it boils down to the security of this compression function. So if this compression function guarantees all the previous 5 properties, then your overall SHA function or the hash function that provides all the features. Okay, so this is the standard hash function that is used in the present day blockchain transactions. Any questions until this point? Anybody?
In your next slide, have you any kind of Merkle tree discussion?
Pardon, I didn't get you.
Merkle tree discussion. Do you have next slide?
Regarding
Merkle tree.
Yeah.
You have in next slide.
Yeah.
Okay. No,
this has been discussed before.
Oh, actually, I missed one.
Okay, so the next, any other questions that you have? Okay, so now we are going to discuss the hash pointers and their application. So basically, what is a hash pointer? A hash pointer is a data structure that is very useful in many of the systems that we discussed about. Okay, so a hash pointer, what is it? A hash pointer is basically simply a pointer to where some information is stored together with the cryptographic hash of the information. Okay, so what is stored? The data is stored along with the cryptographic hash of that data information is stored. Okay, so that is the hash is associated with the pointer itself. Okay, so I repeat, a hash pointer is simply a pointer to where some information is stored along with the cryptographic hash of that information. So whereas if you consider a typical pointer in C, a regular pointer, it gives you a way to retrieve the information, but a hash pointer, it also gives you a way to verify or to ensure that the information that has been stored, that has not been changed or that has not been tampered with. Okay, so this is a guarantee that is given by a hash pointer. Okay, in addition to pointing to where the data is stored, it gives you guarantee or it gives you a mechanism to verify that data that it is pointing to, it has not been changed. Okay, that is in addition to pointing, that is in addition to storing the address, it also stores the hash of the data that it is pointing to. Okay, so we can use the hash pointer to build all kinds of data structures. Okay, so we can use the pointer-based data structures such as a linked list or a binary search tree and implement it with hash pointers instead of pointers as we normally would. So basically in this figure, we built a linked list using the hash pointers. Okay, so we are going to call this data structure as a blockchain. So in a regular linked list, okay, you have a series of blocks where each block has a data as well as a pointer to the previous block in the list. Whereas in a typical blockchain, the previous block pointer will be replaced with a hash pointer. So in this case, each block not only tells us where the value of the previous block was, but it also contains the hash digest of that value that allows us to verify that the value has not changed. Okay, so we store the head of the list, which is just a regular hash pointer, and it points to the most recent data block. Okay, so this is stored in, so this is the structure of a typical linked list. Okay, so it is a typical structure of a typical linked list. So in a blockchain pointer, the previous block pointer will be replaced with the hash pointer. Okay, and each block, it tells you, okay, where the value of the previous block was, and in addition to that, it contains the digest as well. That means in addition to the address, it stores the hash of the entire data of this block. So the hash of this entire data block is stored over there in this hash over here. Okay, so as to ensure, so this ensures the tamper evidence property of the blockchain ledger. Okay, so if a data has to be tampered, for instance, over here, so suppose if an adversary, if he wants to tamper a record or a data in this block, okay, then as he has tampered this data, then in the verification process, okay, then this tampered data will not, the hash of the tampered data will not match with this hash value. So the attacker, what does he need to do? He needs to tamper this hash value as well. Okay, so suppose he tampers this hash value such that the hash of this tampered data matches with the tampered hash, then as he has tampered the hash value over here, that means this hash value is also a part of this entire data. That means this entire data has also been tampered now. Okay, so to escape the detection, okay, what does the attacker do? The attacker then needs to tamper the hash of this block as well, this entire block as well, and that hash is stored in the pointer that is pointing to it. Okay, then that means if it is a large linked list structure, then the attacker has to tamper all the blocks so as to escape the detection. Okay, but ultimately, as he does not have the access to this genesis, okay, so to this genesis, so this is called the genesis block, and the hash pointer, okay, the access to this pointer value is not given to the user. So when he tampers this data, okay, at this point he gets caught because he does not have access to the corresponding hash. Okay, so if an adversary he modifies the data anywhere in the blockchain, it will result in the hash pointer in the following block being incorrect. Okay, so he will get caught. So he will get caught in this process. Okay, so this blockchain construction is similar to the Merkle time card construction. So the block at the beginning of this linked list is called the genesis block over here. So this is the typical structure of a block in a transaction. So the blocks, so the transactions, they are basically the leaves in this tree. So this is called a Merkle tree kind of a thing. So in this Merkle tree, what happens is that the transactions are there at the leaf node, and then this transaction, each of these transactions are passed to this SHA-256 function. So these hashes are then combined to form. Okay, so each of these respective hashes are passed through this through SHA-256, and and then the parent child, and then the parent node is formed. Okay, so similar such other trees are formed over here. So a set of transactions, okay, they lead to the creation of this tree. Okay, and this block, that is the ledger, the ledger stores the root. That means it stores the address of the root address of this tree along with the hash of the respective child nodes. In addition to it, it stores the nonce. So nonce is required for the puzzle solving by the miners, and in addition to the timestamp when the block was created. Okay, as well as the pointer to the previous block. Okay, so this previous hash. Okay, so this blockchain is basically so this blockchain is basically a Merkle tree. So you can think of this blockchain as the Merkle tree. So in a Merkle tree, the data blocks are grouped in pairs, and the hash of each of these blocks is stored in a parent node. So the parent nodes are in turn grouped in pairs, and the hashes are stored one level up in the tree. Okay, and this continues all the way up. So this is called the Merkle tree. Okay, so basically over here, so basically we now have the ability to traverse down through the hash pointers to any point in the list. So this allows us to make sure that the data has not been tampered with, because as we saw with the blockchain, if an adversary tampers with some data, so suppose so this data lies over here in the leaf node. So if any of this data is tampered with, then the hash, then when the tampered data is passed through the SHA-256 function, the output of SHA-256 function will not match with its corresponding hash. Then that means the adversary has to tamper with the respective hash values as well. That means he has to tamper this entire path until the root. But he cannot tamper the root because the root is already there in the block, in the ledger. So he cannot tamper this root. Okay, so this is how. So basically, if an adversary, if he tampers with some data at the bottom of the tree, then that will cause the hash pointer that is one level up to not match. And even if he continues to tamper with this block, the change will eventually propagate to the top of the tree, where he will not be able to tamper with the hash pointer that we have stored. So again, any attempt to tamper with any piece of data, that will be easily detected by just remembering the hash pointer at the top. Okay, so hence it imparts the data integrity aspect as well. In addition to it, okay, we have the proof of membership. So another nice feature of this Merkle tree is that, unlike the blockchain that we built before, it allows a concise proof of the membership. So say that someone wants to prove that a certain data block is a member of the Merkle tree. Okay, so as usual, we remember just the root. Then they need to show to show this data block and the blocks on the path from the data block to the root. That is, he needs to traverse down through this path only. Okay, so we can ignore the rest of the tree. Okay, and hence that means, or in other words, if there are n nodes in the entire tree, then only log of n items need to be shown. And since each step just requires computing the hash of the child block, okay, then it takes about log of n time for us to verify. Hence, verifying the existence, that is the proof of membership or the provenance aspect, okay, it takes a log of n time, where n is the number of transactions that has been there. Okay, that means what? That means even if the Merkle tree contains a very large number of blocks, we can still prove the membership in a relatively small time. Or in other words, the entire verification process of the data integrity or the proof of membership, this verification process, it runs in time and space that is logarithmic in the number of nodes in the tree. Okay, so similar to the proof of membership, we have the proof of non-membership as well. So to establish the proof of non-membership, what you can do is that you can sort all this data, okay, and then accordingly construct the Merkle tree. Okay, and then to prove the non-membership, you need to find the next smaller data and the next larger data, and you need to show that these two data are indeed the siblings. That means they are the children to the same node. Okay, so if you are able to find out the next smaller data and the next higher data, which are siblings, then you can, that implies as a data that has been claimed, that data is not there in this tree. So this is called the proof of non-membership. Okay, so you can use a sorted Merkle tree to establish the proof of non-membership. That is, you need to show a path to the item that is just before the item in the question that is there, and the item that is larger than it. Means you can sort it in the lexicographical order, or in the ascending or the descending order if the transaction has a certain monetary value or a numerical value associated with it. Okay, so if these two items are consecutive in the tree, then this serves as the proof that the item in the question is not there in the tree. So more generally, we can use the hash pointers in any pointer-based data structure that has no cycles. Okay, you start at the root node and then gradually approach towards the leaves. Okay, a typical application is the directed acyclic graphs. Okay, so the next property that the next cryptographic primitive that we come across is the digital signatures. Any questions until this point? Audience? I'm unable to unmute.
Priyanka, Iman, ask your question.
I'm unable to unmute.
Yes, sir. Now we could unmute ourselves because the host control was earlier. Sir, the mail what the genesis anybody could
I'm
answer
unable to hear you.
Is it possible in the genesis?
I'm unable to hear you. Your voice is breaking. Yeah.
Yes. Now.
No,
Hello?
your voice is breaking. I'm unable to hear you.
Oh.
I'm not sure whether there
You
is a
can write
network.
in chat, madam. If there is a problem with the microphone, you can write in
Hello?
chat.
Hello, you can put your question in the chat as well. I'm not sure that whether there is a network bandwidth problem at my end or at the audience.
Okay.
Can you repeat your question
But I
again?
could hear you properly, sir.
Now your voice is okay. You can ask.
Okay.
Okay. Not able to get. Fine. So I proceed with so we proceed with the next next topic, that is the digital signature scheme. Okay. So this is the second cryptographic primitive that we talk about. Okay. So basically a digital signature, why is it required? A digital signature is supposed to be the digital analog to a handwritten signature on paper. So that is we desire two properties from any digital signature that corresponds to the handwritten signature. The first is only the user should be able to make his or her signature and nobody else, okay, who nobody else should be able to forge it. And the other property is that anyone who sees that signature can verify that indeed is a that it is indeed a valid question. So we have the question over here. So this person okay, so the question by Priyanka is that can we tamper the Genesis block? No, it is not possible to tamper the Genesis block because as I told, even if you tamper the Genesis block, you cannot tamper the hash pointer that points to the Genesis block, because that hash pointer is stored in the public ledger. Okay, and that is also guaranteed by the hash tree. Okay, so that is stored as the linked list. Okay, so hence you cannot tamper the Genesis block. Even if you tamper the Genesis block, that will get caught, because the tampered data, the hash of the tampered data in the Genesis block, that will not match with the hash pointer. Okay, so hence even if you tamper the Genesis block, that will easily get caught. Okay, the next question is, can you explain the puzzle friendliness property? Okay, so this puzzle friendliness property, it says that over here, what was it? So this puzzle friendliness property, yeah. Okay, so in this puzzle friendliness property, it says that suppose to a miner or to any adversary, okay, if that adversary is given the puzzle ID, okay, and if he is given the hash function itself, so suppose the SHA-256 is used, okay, so suppose the adversary or the miner knows that the SHA-256 is used, he is given this input, this ID value, and suppose he is given the entire set, that is the solution set. So given these three parameters, okay, the adversary or the miner's aim is to solve the puzzle. So what is the puzzle? The solution is to find the correct value of x. Okay, that is he needs to find the correct value of x, which when appended with the ID, and if this appended value is passed through the SHA-256 function, then the output of the SHA-256 function should belong to this set y. Okay, so initially when this when the traditional blockchain systems were proposed, that is in Bitcoin, this set y was initially very large, and with the advent of time, this set y, the cardinality of this set y is made smaller and smaller. Okay, why? Because reducing the cardinality of this set y, that means you are reducing the solution space. That means you are making it much harder for the input x, okay, to get to the solution space. Okay.
Sir, I have one question regarding that nonce value I asked you. Hello. Hello, sir. Hello. Dr. Majumdar, can you hear me?
Hello.
Can you hear me? The mic was muted.
Yeah.
Okay, so actually I was asking about nonce value. When suppose in Bitcoin or any kind of blockchain where proof of concept is used, proof of work is used. So the nonce value is decided by the miners. Okay.
Right.
And that you can say this is a war of tag kind of thing. That many miners are working. Okay.
1 minute. 1 minute. Can you give me a break? 1 minute. I'm just coming. Hello. Hello. Yes, Dr. Mukherjee. Yes.
I was asking that suppose more than one miners are working for validating on block. Okay. So on the basis of timestamp, this suppose a miner can add that block, or that is based on the number of leading zeros
Yeah,
as value.
yeah,
This is my one question. So
yeah. So that means if you increase the number of zeros, that means the number of non-zero bits, okay, that is gradually reducing.
yes, sir. Yes, sir.
Okay, so the overall sample space means the solution set that is gradually reducing. So that makes this puzzle solving even harder. That means you need to hit upon a value that is now even from the smaller set. That means as you increase the number of zeros, that means that means the final solution set that is becoming much smaller and smaller, isn't it? For instance,
Yes.
that means if you have 10 non-zero bits, that means the sample size is 2 raised to the power of 10. The solution space is 2 raised to the power of 10. If you have 9 non-zero bits, then you have the solution space 2 raised to the power of 9. So you need to hit upon one of those values in the 2 raised to the power 9 values. So that's why your puzzle solving becomes even harder in this case.
Yes,
As you increase the number of zeros.
My question is that suppose two miners are coming up with the two different blocks, like two different hash values. Okay, and one miner is having more number of leading zeros than the second one. So which block will be added? Which block will be added for long actually?
That will have a smaller number of non-zero values.
That will.
Yeah.
It doesn't depend on the timestamp.
Means it will depend upon the timestamp as well, because you have the problem of double stamping as well, double spending problem as well. So you need to solve the double spending problem. That timestamping also will also be taken into account. But
Okay.
usually it happens that the preference is given to the smallest matching.
Okay. Okay.
So it means that which has the larger number of zeros.
Okay. And other regarding that Priyanka, Dr. Priyanka or Mrs. Priyanka, don't know. She asked about that Genesis block, that we can temper the Genesis block or not. So
Yeah.
does Genesis block contain any kind of transaction, or it's a block only having initial hash values or some kind of thing?
No, that is the transaction block only. That is
Transaction block.
yeah.
Or it contains valid transactions also.
Yeah. But the block that is there means that will comprise. No, I don't think so. It will comprise the hash values of the child nodes. It will just comprise the hash values of the child nodes. I think so.
Okay. Okay. Thank you, sir. Thank you. Yes.
Okay. So the data signature. Okay, so this data, so this digital signatures. So in this, the first property is that only you can make your signature, but everybody else, that means every user node in the network who sees that signature should be able to verify and establish its validity. The second property that is required is that we want the signature to be tied to a particular document, so that the signature, it cannot be used to indicate your agreement or endorsement of a different document. So for handwritten signatures, this later property, it is analogous to ensuring that somebody else cannot take your signature and snip it off and remove it off from one document and put it onto the bottom of another document. Okay, so these are the two important properties that we want from the signatures. So how can we build this? So how can we build this in a digital form? So according to a typical public encryption scheme, there is this key generation algorithm that takes in the security parameter, that is the key size, and it generates a pair of keys, that is the secret key and the public key. The public key is put it into the public database, okay, from which all other users in the network can gain access to. Okay, and the secret key that is kept private. Okay, and it is used to sign the messages. Okay, then you produce the document or the message and you sign it with your secret key. Okay, so the sign method, it puts a signature under the secret key escape. Okay, and then verify, and this verification, of this of this document, that is the verification of this signature is established by the public key of the person who signed it. Okay, so this verify, it returns a Boolean value. Okay, so it will return true if the signature is a valid signature, or it will return false. Okay, so this verification is done with the public key of the person who has signed it, or the entity who has signed it. So there are algorithms. So the first algorithm is the generate key or the chain keys. That is a randomized algorithm. The signature is also a randomized algorithm. Okay, and the verify function, that is a deterministic algorithm. So the security properties of typical digital signature schemes are as follows. That is once a document has been signed with the secret key, if this is verified with the public key of the entity, the verification should give you the true value. The signatures should be existentially unforgeable. An adversary who knows the public key gets to see the signatures on the messages of his choice. That is, he can produce verifiable signature on another message. Okay, so what does typical adversaries or the attackers do? They try to play this unforgeability game. So what happens is that for this challenger is the one who signs the document. Okay, so for this challenger, the public key encryption scheme, it generates the secret key, a pair of keys, that is the secret key SK and the PK. Okay, so now the attacker, he creates one document or a message, say M0. He asks the challenger to sign that M0 with his secret key. So the challenger signs that document M0 with the secret key SK. Okay, that attacker now has a message along with the signature put by the challenger. Then he creates a set of more documents or more messages. Okay, and this challenger signs all those messages with his secret key. So the attacker now has pairs of messages along with the corresponding signatures. So now from all these pairs, the attacker tries to create a new signature M, which is not there already. Okay, and he tries to produce a signature. Okay, so now the challenger, he tries to verify that whether the signature, whether the signature in fact passes this verified test or not. If this verified test is passed on, it gets passed by passing on this message M, this corresponding signature and his own public key, then it is concluded that the attacker is able to forge the challenger's signature. So this is the unforgeability game. Okay, so that means for digital signature scheme to be secured, this unforgeability game, okay, should always return the false. That means the attacker should not be able to win. Okay, for any number of messages that he gets access to and the corresponding signatures. So practically speaking, the algorithms must be randomized, should be randomized, and there should be a good source of randomness. Okay, there has to be a limit on the message size. So usually, what happens is that the typical digital signatures on the blockchain transaction, the messages are provided on the hashed outputs, because the hash can take messages of infinitely large size, but the hash outputs are of finite size. So hence, digital signatures can be easily put on those hashed outputs. Okay, so to increase the message size, what do? You usually sign the hash of the message rather than the message itself, and that hash has to be collision resistant. If it is not collision resistant, then for two different documents you can produce the same signature, and that will be very harmful to the security of the system. Okay, so what is usually done is that you usually sign the hash pointer, that is the pointer that points to the entire Merkle tree. Okay, so the signature covers the whole structure of the blockchain itself. So Bitcoin, okay, it uses the elliptic curve digital signature algorithm. So this is the most standard digital signature algorithm that has been put to use in the present day blockchain applications. Okay, but the bottom line is that good randomness is absolutely essential. Okay, so if you hold up or if you mess up the generate keys, that is the key generation algorithm or the signature algorithm, then it becomes easily forgeable. So here are the parameters of the elliptic curve digital signature algorithm. It is a US government standard now, and it has been analyzed over its security properties have been analyzed over the years and have been believed to be cryptographically secure. And it adopts the standard elliptic curve, that is SecP 256K1. The following are the parameters for this elliptic curve digital signature algorithm. It takes in a private key 256 bit. So this private key of 256 bits is used to sign the message or the document. The public key, that is of 512 bits, is used to verify that document, and the message that is signed is typically of 256 bit. So this message is nothing but the hash of the original document. So that original document or the file can be a very large file. Okay, so that file is passed on through the SHA-256, and the output of the SHA-256 is the message that is signed. So that's why the message to be signed is basically of 256 bits. The signature is of 512 bits. The digital signature is of 512 bits. That is, the elliptic digital signature algorithm is defined only for 256-bit long messages. Okay, so in digital signature algorithm, we use the public keys as the identity of the person in the system, because the public key can be accessed from the public database. That means that public key can be used as the identity of the person instead of using the person's private credentials. Okay, and you create a new identity using the generate keys function. So this is all about the hash function and the digital signature scheme. So I would like to stop at this point. If the audience have any questions, then please ask. Anybody?
Hello, sir.
Yes.
The thing which I asked regarding cryptocurrencies and its use, how the cryptocurrency with the incentive, how it will function. Can you elaborate it on Ethereum and Bitcoin for this?
That I don't have the knowledge regarding the Ethereum. Maybe it will take another session. So at this point of time, I'm unable to explain it regarding the Ethereum.
Okay. Okay.
Hello, Miss or Priyanka, Miss Hema. Hello. Yeah. What was your question?
So the incentive-based cryptocurrencies.
Incentive based, actually, I understood your question. I know I can answer a little bit about it. That blockchain of the Bitcoin came first. Okay, with the invention of Bitcoin in 2008 actually. Okay, so in that case, no, actually you cannot, like in cash. What we do, we can print cash. Okay, in Reserve Bank print cash kind of thing. But in Bitcoin, you cannot generate cash. So to create coins, the coins are created by mining the blocks. Okay, like when a miner validates one block, in the system he can create some coin out of it. Okay, so that is called incentive in Bitcoin. So similar kind of incentive is used also used in Ethereum. Okay, so whatever little bit
both have the technology of blockchain behind the use of this cryptocurrencies, right?
Yes.
Sir, we are using the blockchain technology in our banking sector. The same question which I asked a bit earlier to the speaker is the same. What is in the banking sector? We using this incentive-based cryptocurrency. Can we have a common man to access in this? Is it really a challenging one in India to deploy this?
No, actually the main problem in Bitcoin and this cryptocurrency is that the implementation and the regulatory law of a country. Okay, so every country is having different kind of financial laws. So this Bitcoin and all this actually invented based on some assumption. If there is certain laws which does not allow using this kind of cryptocurrency, then it is difficult in the country. So that's why the new bill is coming in the Indian Parliament. Okay, regarding this Bitcoin, this bill is being actually in the formation stage. Okay, so very soon it will come. Then
we were aware of it, sir, because initially they were not allowing, the law was not allowed to use the cryptocurrency kind of thing. But now they are making a law to a certain extent. In certain sectors, they are allowing this options to have a incentive-based cryptocurrency. So that's the reason I posed this question to the speaker. The way they ask regarding this deployment of the blockchain, because the NITI Aayog of India, which is having a concept of implementing the blockchain technology in various sectors like agriculture, banking, and healthcare. Any of the sectors, India is having a 2020 to 2030. That is the one they are taking as the Internet of Value and implementing same India project by the NITI Aayog of India. That's the reason I'm posing this.
No, but madam, actually the thing is that for different field, that incentive based thing is not actually workable. Okay. So basically for cryptocurrency and all, the incentive based technology is going on. But for like blockchain is being used everywhere, like in agriculture, you are saying supply chain and many fields. Okay.
Yes.
This incentive based technology will not be workable. Okay. There are different kinds of technologies, different kind of consensus rules and all being implemented together. Okay. It is not that everywhere where you are using blockchain that you have to use this incentive and all or kind of coins and all. Okay, there will be different kind of algorithms.
That's the reason I'm asking that whether they can have if they are implementing blockchain also, how a common people being a miner could have a solution by finding solution to hash functions, right? That would be a major challenge for any common people.
Yes, that's why there are different kind of blockchain like private, public, permissionless, and permission blockchain. Okay. So in this kind of applications like you are saying about like in banking sector, cryptocurrency, all kind of thing will be used. So their incentive can be used like for agriculture or supply chain. To whom you will be giving this coin or why actually? There is no use of any kind of coins and all. Okay.
Yes. There are people who are not aware of this technology as well, right? So for them, how we could implement it? That is the question I'm posing here. In the various.
That's why this is a new technology, na? So we are trying to learn many things, but the thing is that whatever available on the internet and few experts like Dr. Mujumdar and all, okay. So this will come gradually actually. Okay. Not everything is clear.
So that's the reason from 2020 onwards, they're taking it as an Internet of Value and implementing Sane India concept, which was initiated by our Prime Minister Narendra Modi ji. That's the reason I just posed the question out of interest so that I could know, I could be knowledgeable by the speaker of IIT Indore, who is a very good presenter over here in this section. So I just had a curiosity to know about it because my research area is this one.
Okay.
Thank you, madam.
Okay, thank you, sir.
So anybody having any question, please ask. One, Dr. Mujumdar, one participant has asked in the chat box, can ebook issue return be managed securely in online environment with blockchain?
Yeah, of course, Miss. Yeah, of course, Miss. See, Miss, any transaction, Miss, whether it is a ebook issue, Miss, basically ebook issue or return. Okay, so that is also, Miss, there is also, Miss, this is also a transfer of asset, right? So transfer of asset means, Miss, first is the information transfer, and then you have the asset transfer, and then you have the recording of the transaction. That means you need to it needs to be guaranteed by the public encryption scheme. That is, first is you need to be able to correctly encrypt. Okay, you need to apply a suitable public encryption scheme to encrypt the resource, and then you need to and then that the sender or the receiver, they needs to be authenticated. Okay, so this authentication can be done via this digital signature scheme. Okay, the issuer of the book, he can send a message along with the message. He can provide his signatures. Okay, so the signatures he can use by using the secret key by using his secret key. Okay, so using his secret key, he can encrypt and provide the signature to that message, and that signature can be easily validated by using the public key of the person who has signed the document, and then that resource can be released. The resource, that is the ebook, can be released, okay, by applying a suitable public encryption scheme. So if the encryption scheme and the corresponding digital signature scheme, if they are guaranteed, then you can have a secured ebook issue return system.
Okay, thank you, everybody. Thank you all participants now. So,
Sir?
Dr. Majumdar,
Sir, actually,
thank you for giving your
recording
time.
session.
Yeah, I have all the recordings. I'll be sharing the link. No issue at the end of this FDP. Okay.
Okay.
Oh,
So, thank you, sir,
Thank you.
for being with us and giving your time. Okay.
Yeah.
So,
Sorry, there have been some intermissions from my end. Actually, there were some phone calls.
No issues.
There was throat problem as well.
These are things you have to accept in online mode actually.
Okay.
Okay, thank you, sir.
Thank you.
Okay.
Thank you.
Thank you, participants, for today's session, and then tomorrow we'll come back again. Okay, we'll gather together and learn new things from other experts. Thank you.
sir?
Yeah.
The quiz question will be posted on Friday itself.
Quiz. Yeah, that's a test, online kind of test. I will be sharing Google link, Google question kind of MCQ kind of question. Okay.
Okay.
So from that link, you can answer your questions, and then we'll be able to accordingly. Okay.
Oh, thank you.
So in the session actually schedule, you can see the time we have given for test.
Sir, the time schedule what you have given is Friday 3 to 4 p.m. You have mentioned there. I have seen the schedule, but the thing
Yes.
is that day that slot I do have a examination duty, which is going on in the Karnataka Visvesvaraya Technological
Madam,
University.
in that thing, I cannot do anything. Okay. See, I don't know. Actually, every day may happen. You have to manage, madam, somehow.
Oh,
Okay.
only 3 to 4 will be the session time
Yes,
for
yes.
the question.
Yes.
Oh,
Thank you. Thank you for today. Bye.